This is Dr. Kavita Singh, Associate Professor, Institute of Aeronautical Engineering. So today we are going to discuss, our topic will be height measurement by stereoscopic parallax. So how do we measure a height of an object by using the stereoscopic parallax? So in the previous lecture, we have just discussed what is a stereo pair. So what is a stereo pair? Stereoscopy. So this, with the help of the stereo pairs, with the help of the stereo photos, how can we measure the height of the object? Height of the object in sense, the objects on the ground, like we have buildings, we have trees, we have different types of structures. So if you want to measure the height of that particular building or structures, how can we do? So that we can do with the help of the stereo pairs, with the help of the stereo pairs photos. And that is, we do it with the help of the stereoscopic parallax too. So first we have to understand what is stereoscopic parallax. So before that, just these are the contents which we are going to discuss in this entire topic. So before we understand how we compute the height of the object, first we have to understand what is stereophotography, what is stereoscopic parallax, what is differential parallax, average photo wavelength, parallax measurement, and finally, you will come to know that how we can compute the height of the object by stereoscopic parallax. So let us understand what is stereophotography. Stereophotography. So stereophotography is like it's a adjacent but overlapping aerial photo are called stereo pairs and are needed to determine parallax and 3D or stereo or 3D. So here, if you see in this photo, we are having two photos, photo 1, photo 2, photo 1 and photo 2. So these two photos are, you can see here, this is the flight line direction which is going like this. Now here you can see this is the flight line direction which is going like this. So in the previous lectures, we have already discussed like how a flight line goes in a direction either east to west or west to east, and either south to north or north to south. So while going in a direction, it keeps on clicking a photo in a same forward direction. So suppose it has clicked a photo like this. This is one photo and this is photo number 2. So we will see that always in a same flight line direction, when the photo number 1 and photo number 2 is generally clicked, there will be overlap. So this overlap area is this area. So in this photo also we can see this is the overlap area. So this overlap photo is used for determining the stereo vision. Stereo vision means 3D vision. So once we keep these two photos aligned together and with the help of the stereo pair, we are able to see the 3D in this portion, 3D in this area, 3D vision in this area. So it will show you the 3D vision with the help of the stereo. So always, if you want to check about the 3D vision, if you want to see the 3D illusion, then we have to take a stereo pair photo, and that too from the same flight line direction. Like photo 1 and photo 2, we have to take, or photo 3 or photo 4, we have to take for the stereo vision. So stereo photography is the adjacent photo but overlapping photo. You can see here adjacent but overlapping. So it should be adjacent means one photo should be here, the other photo should be here. So it should be adjacent to each other. That means the topography which we can see in this photo, the continuity should be there in the photo 2. So this is called as the adjacent photo. So suppose there is a road here, from here to here, the same road should be continued in the other photo. So this is called as adjacent photo. But there will be some overlapping area, like suppose this road you can see in this photo. So this same road we can see in this photo also. So once you just keep this photo 2 on over the photo 1, so some portion will be overlapped. So this portion we have a overlap area. So this photo is only required to see the 3D vision, and further we can determine the height of the object with the help of these photos only. So now let us understand about this stereoscopic parallax. What is this stereoscopic parallax is? Now to create a stereoscopic parallax, we need a stereo photos. So in the previous slide we have seen stereo photos are the photos which are adjacent but overlapping. So in the stereoscopic parallax, the displacement of an object caused by a change in the point of observation is called as parallax. Change in the point of observation means, suppose you can see this is the ground and this is your left eye, this is your right eye. So here the point of observation will be here, and for the light right eye, the point of observation will be here. So this eye will see the image from here to here, and this eye will see image from here to here. So both the images will be different. The point of observation will be different. So you can see in this from here, it is visible from this portion is more and this portion is less. Whereas here, this portion is less, this portion is more. So the point of observation differs in a photo from our eyes also. Once we see with our eyes from left eye, the point of observation is different. From right eye, the point of observation is different. Same like when the flight goes in a direction, in this direction. So suppose the flight is somewhat here. So the nadir point will be somewhat here. So this is your nadir point. This is your nadir point. And the flight has captured the area. Flight has captured the area from here to here. Okay. So this portion is captured. This is your nadir point. This is your principal point will be somewhat here. So it has captured from here to here. Again, when the flight moves, suppose your flight position is somewhat here. So it is capturing the information. Now the nadir point will change. Now the nadir point is here and it captures the information from here to here. Okay, so point of observation when changes, then only we are able to see the displacement. So the displacement of an object caused by a change in point of observation is called parallax. So it's like the displacement of the object while the change in the position of the point of the observation. So always the point of the observation happens when the flight moves in a direction, and when it changes its position from where it is clicking the photo, from there wherever it clicks the photo, the point of observation changes and the displacement occurs. So higher the object, like if the object is having more height, the more the displacement will take place. So stereoscopic parallax is caused by taking photographs of the same object but from different points of observation. This is called as stereoscopic parallax. Now for observing a stereoscopic parallax, we have to take the stereo pairs of photos. Stereo pair means adjacent but overlapping photos of the same series, of the same flight line direction. Now, this is the same image what we have seen in the previous picture. So this is the left image, this is the right image. So this is your left eye and right eye. So once you see from your left eye, the image will be from here to here. This is the image is from your right eye, the image is from here to here. So the displacement of an object caused by the change in the point of observation is called as parallax. So stereoscopic parallax is caused by taking photographs of the same object from different points of observation. That is what called as the stereoscopic parallax. Now see here we have one more example of stereoscopic parallax. Like we have a pencil here, you can see a church or a building is here. Now what your right eye sees is somewhat here. The church you can see here, pencil you can see here. But whereas when you see from your left eye, the pencil will be visible here and the church will be visible here. So pencil is very displaced because it is close to observe. Church is less displaced because it is further away. So closer the object, the displacement will be more. Now here we have one more example. The same principle can be used to find the height of the objects in the stereo pairs of the vertical aerial photographs. Now you have two photos here. This is photo 1. This is photo 1. This is photo 2. So we have two photos again, photo 1 and photo 2. So in photo 1, what is the difference you observe? So there are, these are the same image, but there is a difference in the image. When you see, observe clearly. So here in this building, you see this is the top view of the building. And this point of observation is somewhat here. This is the observation point. This is the observation point. and for this photo, here is the observation. Okay, so observation point for the left photo is here. Observation from for the photo number 2 is here. So now this is your flight here. So when it clicks the photo, it has captured from here to here, right? So it has captured this building side. This is the side of the building. This is the top of the building. Whereas in this photo, this side is not visible in this photo. This side is not visible in this photo. Whereas in this photo, you see the other side is visible. This side is visible, top is visible, and the right hand side is visible. So this is the difference. It is the same photo, but it has a difference of the point of observation is different. So if with this point of observation, we can see in this building also there is a front view of the building and the top view of the building. Whereas here, the point of observation changes again. So we can see very less front view. This side view is visible here, but in this side view is not visible because the point of observation is here, and here the point of observation is here. So this is the difference. So this is called as parallax. Parallax means displacement of the object, with a different point of observation. This is called as parallax. Now, stereoscopic parallax. Now, this is very good example. It is clearly visible in this example. So, note the displacement between the top and the base of the storage towers in this photo. Stereo pair. So, this is a stereo pair. Stereo pair, why we say this is photo 1 and this is photo 2. So, photo 1 and photo 2, you have same photo here, but your flight line direction, this is the flight line direction. So when your flight is somewhat here, so this is your capturing point. So it has captured this much area. Now the flight is moved here. Okay, so it has captured from here to here, right? Now what is the difference here? See this, observe this tank. This tank top is visible and the side is also visible. This tank top is visible and the side is also visible, right? Whereas in this photo, you can see only the top is visible, but side it is not visible. Side only we can see the shadow, right? So this is almost a vertical photo. This is almost a vertical photo, whereas this one is a oblique photo. Oblique photo. Why? Because we can see the side of the building and we can see the top of the building. Whereas here in photo number 2, you can see only the top of the building. So this is called as the parallax, means point of observation is different. Here, point of observation is somewhat at this point, and in this photo, point of observation is somewhat here. That's why there is a difference between the point of observation. So this is called as stereoscopic parallax. So the image displacement will happen due to the point of observation when it differs. Now, there is another term, we call it as differential parallax. So what is differential parallax? So differential parallax, same here, photo 1, we have photo 2, we have photo number 1 and photo number 2. So differential parallax is a difference between the stereoscopic parallax at the top and the base of the object, So for example, in photo number 1, suppose this is the principal point and this is the principal point for photo number 2, and this we have the object which we are going to measure the height. This is the object instance, we are going to measure the height of this tree. So here we have this object in this photo. So the displacement, what we can see here in this photo, it will be, this side will be visible and this side will be visible. Whereas in the photo 2, this side is visible and this side is visible. So what we have to do if you want to find out the differential parallax means the value of the differential parallax, then how do we find out? So what we have to do, we have to just keep this photo side by side. So in this photo, what we have to do is just you have to measure the base length. So what is the base length means? This base and this base, from here to here. Just measure the distance from here to here. That is from photo number 1 to photo number 2. What is the base length? So this is the base length. Okay. Photo number 1 to photo number 2. This is the base length. So that is we have measured as 15.2 mm. Okay. Now we have to measure the top. Top means this top and this top. That is top of the tree, top of the tree. So what is the the value of this is 13.5 mm. So once we have to, if you want to know the differential parallax, what is the differential parallax? What we have to do is just you have to measure this two distance and then suppose it is 15.2 mm minus 13.5 mm we have to do. So finally the differential parallax what we get is 1.7 mm. So this is how we get to know about the differential parallax. These are the terms once we understand, then only we are able to understand about the computing the height of the object. The differential parallax we know, what is a parallax we know. Now we have to find out what is average photo base length. So what is average photo base length? So these transferred points are called transferred principal points or conjugate principal points. The line segment joining the principal points and the conjugate principal points constitute the flight line of the aircraft, also called as baseline or A-base. So average photo base length, how to find out the average photo base length? Suppose this is photo number 1 and this is photo number 2. Photo 1, photo 2. Okay. Now in this photo, this is our principal point. So principal point, how to find out? We have to join all the fiducial marks. Then the center of the photo is called as principal point. Now in this photo number 2 also we'll join all these 4 fiducial marks. So the center of the photo is called as principal point. Okay. So photo 1 and photo 2 principal point you know. Then what we have to do, if your object is somewhat here in this photo, so what we have to do, this object we have to mark as CPP. CPP is conjugate principal point. CPP. CPP. Okay. So CPP here, CPP here. Now later what we have to do, once you, this is the area which is overlap area. This is the area which is overlap area. So once you keep this photo over this two overlap area will be merged and finally the CPP point will be somewhat here. So this is why this conjugate principal point, how to find out this average photo base length is, for example, photo number 1, distance between principal point to conjugate principal point. Now what we have to do, we have to find the distance. Now what we have to do exactly? So your CPP is somewhat here. Your CPP is somewhat here. CPP somewhat here. So what we have to do now, we have to find out the distance from principal point to CPP. Okay, from principal point to PP to CPP. Okay, so the distance between principal point to conjugate principal point for photo number 1. Now photo number 2, distance between principal point to conjugate principal point for photo number 2. So suppose for example photo number 1. So your photo number 1, the distance from PP to CPP, from principal point to the CPP is 9.5 centimeters. Now for photo number 2, your principal point to CPP, from PP to CPP, this is 9 centimeter. Okay. So how do we find out again? So 9.5 plus 9 centimeter. Then later what we have to do is 18.5 divided by 2. Divided by 2, we'll get the average photo base length. Average photo base length. Okay, average photo base length. So this is how we find out the average photo base length in a photo. Photo number 1, photo number 2, principal point, the distance from principal point to distance to CPP. So photo number 2 also, distance from principal point to CPP, that is conjugate principal point. Then later we have to add these two values and then we'll get the total of these two values divided by 2. Then we'll get to know about the average photo baseline. Now we know about the stereoscopic parallax, we know about the differential parallax, we know about the average photo baseline, and we know about the stereoscopic parallax. Based on all this, we can just find out the height of the object. Now, the same example is given here. The principal point, center of the photo, CPP is conjugate principal point, adjacent photo PP. So here clearly we can understand this is your PP and this is your CPP. This is your CPP and this is your PP. PP is what? Principal point. Principal point to CPP. So this is the distance what we have is 9 centimeter, and this distance what we have is 9.5 centimeter. Okay, so our principal point to CPP we have 9.5 centimeter in the photo number 1, and principal point to CPP is 9 centimeter in photo number 2. Now we have added this 2 and that is 18.5 divided by 2. Then we'll get to know about the average photo baseline. So now parallax measurement. Parallax measurement means how do we measure the height of the object. This is the formula we have, that is height of object. So here we have h into dp, h into dp by p plus dp. Okay, now this is h is the height above the ground. So height of the aircraft above the ground. Height of the aircraft above the ground means suppose this is your aircraft and this is your nadir point. This is your nadir point and this is the capturing area. Now in this capturing area, this is your nadir point for example, and this is your aircraft. Now this is the area captured here. Now above the ground means this is the ground, and from here to here will be your h. H is equal to height of aircraft. Now we have P here. What is P? So P we have discussed this before. So P is the absolute parallax at base of object being measured. So that is the average base length is the P. Now dp. dp is what? Differential parallax. So how do we measure the differential parallax? The differential parallax is like the difference between the base and the top of the object. So base length we have to measure from photo number 1 to 2, and then we have to measure photo 1 and 2, the top of the object. So base minus top will get the differential parallax. So for convenience, the photo base length of stereo pair is commonly substituted for absolute stereoscope. Now computing the height using the stereoscopic parallax. Now here same formula we apply. H is equal to h into dp by p plus dt. So whereas h is object height can be, this is the object which you have to measure, and this object will be in the both the photos. So photo 1 and photo 2. In both the photo we will be having the same object. So if you want to measure the height of this object, so that is h which you have to find out. Now flying height of the object which is already given in the photo. So differential parallax we have to find out. So whichever object we are trying to find the height, we have to just find out the base length and the top of the object, and finally we have to find the P. P is what? Average photo base length. So how to find out the average photo base length? That is distance between in a single photo number 1, the distance we have to measure from principal point to the conjugate principal point. In the photo 2 also we have to measure the distance from principal point to the conjugate principal point, and later we have to just subtract photo 1 minus photo 2, and finally by 2 we have to divide, we will get the average photo baseline. So this is a very good example to understand now. So computing height using stereoscopic parallax. So this is one example given here. Following example is taken from T.E. Everly, G.L. Berlin, 1992, Fundamentals of Remote Sensing and Air Photo Interpretation, Macmillan P. So this is one example taken. So this is how the aerial photo looks like. So if you want to measure this tower height, it's very clearly given here. So aerial photograph will be very high resolution images. So here we'll be getting the top and the base we have to measure with the help of the scale. So same photo we have to take, adjacent photo and overlapping photo we have to take from the same series of the aircraft. Now photo 1 here, photo 2 here. Now we are going to measure, suppose this is the tower we are going to measure. So what we have done here is photo 1 we have taken, photo 2 here. So what is photo 1 here? Photo 1 is these two are stereo pairs. Stereo pairs. Why we call it as stereo pairs? Because these two are adjacent photos. Adjacent photos of same flight line. Adjacent photos of same flight line. Adjacent photos of same flight line. So what is the same flight line means? If this is the flight line direction. So in a flight line direction, the photo number 1 is clicked here and the photo number 2 is clicked here. Now this is the building which we are going to measure the height. How can we compute the height of this building? By using the stereoscopic parallax. So this is building 1. So this is the first view. So in this view, we can see this portion is visible. Top is visible and front is visible. Whereas in this photo, this portion is visible and side is visible here. Because the point of observation is different. Top is visible. So the point of observation is somewhat here. The point of observation is somewhat here. So it can see this side of the building, and here the point of observation is somewhat here. So you can see this side of the building. Now what you have to do, if you want to compute the height of this building, first thing what we have to find out is differential parallax. So what is the differential parallax? So the differential parallax is from base to the other photo base. So the same image, same object you have in photo 2, same object you have in photo number 1. Now what we have to do, we have to measure the distance from here to here. Photo number 1 to photo number 2, that is 2.06 inches. So why it is in inches? Because we generally use the hard copy of the aerial photograph to measure. So if you have a hard copy of the aerial photograph, we have to just take the help of a scale and then we have to measure the base. So that base will be in inches, generally in inches or mm. So that is 2.06 inches. And then we have to measure the top. Top is top of this building. That is 1.46 inches. Now if we want to get dp, so what we have to do is 2.06 minus 1.46 is equal to, we will get 0.6 inches. So this is our differential parallax. This is our differential parallax. Okay, next, this will be the data given. So differential parallax we got. Now to find out this average photo base length. So this average photo base length is already given, that is 4.4 inches. Just now we have discussed in the previous 2 slides that how to find out the average photo base length. That is from principal point to conjugate principal point in photo 1. So here in the photo 2, principal point to the conjugate principal point in photo 2. Photo 1 and photo 2. So here PP to CPP, PP to CPP. Okay. So this difference we have to find out, distance from here to here. So photo 1, distance from PP to CPP. Now photo 2, distance from PP to CPP. Okay. Then photo 1, suppose it is 2 inches and photo 2 3 inches. So what we have to do? 3 plus 2. So we will get 5. 5 divided by 2, we will get the base length of the object. So that will be the average base length of the object. So here already the data is given, that is 4.4 inches from photo 1 and photo 2. So here this is the formula we are going to apply to find the actual height of the building. So in the previous slide we have seen the height of that building which we are going to find out. So H into dP, H is the flying height, where H is the small h is the object height and H is the flying height, that is 4,600 feet. 4,600 feet we have seen in the data. Now differential parallax we got is 0.6 inches and the average photo base length what we have is 4.4 inches. So this two we have in inches, this we have in feet. Now we have to just put on this formula, that is H is equal to 4,600 feet into 0.6 inches by 4.4 inches plus 0.6 inches. Okay, so 4,600 feet into 0.6 inches divided by 5 inches is equal to, we get 552 feet and the true height will be 555.5 feet. So approximately our the building height is 555.5 feet. So we can say 556 feet. So this inch will cancel and our answer will be in feet. So always remember the height of the object will be either in feet, either in the meters, because the actual height we are going to find out here. So with the help of the aerial photograph, by sitting at one place itself, with the help of these methods, we are able to find the height of the object. So we need not go to the actual ground position to find the height of the object. So this is the simple methods how we can determine the height of the object. So in the previous lectures also we have discussed it with the help of the single photograph, that is with the help of the image relief displacement. So this is the other method which we have used here with the help of the stereoscopic parallax. Stereoscopic parallax is one pair of photo with the same series of flight line direction. So that should be overlapping photo from a same flight line direction. So this is how we are able to measure the height of the objects. Now these are the references. I hope you understood how we can measure the height of the object with the help of the stereoscopic parallax. These are the few references we have. That is M. Angireddy. Book we have Remote Sensing GIS from BS Publications, New Delhi. So this is very good book where you can find out the content and we can just go through it. Now we have the other one is Fundamentals of Remote Sensing by the George Joseph. That is from University Press, Hyderabad. And these are different NTPL courses, PTL courses from where we can just find out the content. So here we are some more contents we have from PTL, ac.in. So if we just want to know more information, you can just visit the sites to get the information about this stereoscopic parallax. So that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.